Greetings, math students. It's Mrs. Marcellus and Pythagoras. We're here today to help you learn how to solve problems using ratio tables. Today's learning objective is students will represent and solve problems involving equivalent ratios by setting up and using ratio tables. You think that sounds a little bit intimidating, huh? Well, let's take a look at a couple key phrases in that. Equivalent ratios simply means we're going to be making equal fractions. And using the ratio tables means we're just going to be putting equal fractions in a table form. There is no vocabulary to record today. That makes Pythagoras very happy. Before we begin using the ratio tables, let's first take a look at what it means to create equivalent ratios using some plain fractions. Write ratios that are equivalent to the given ratio. Let's start with 8/14. One way to write equivalent ratios is to divide. This is the same as simplifying a fraction. We can divide both 8 and 14 by 2, and the result will be 4/7. 8/14 is equivalent to 4/7. We also can write equivalent ratios by multiplying. For example, we can multiply both 8 and 14 by 2, which will equal 16/28. Again, we have a pair of equivalent ratios. Another example would be to multiply by 3. This would give us 24/42, which is also equivalent to 8/14. In fact, you can create an infinite number of equivalent ratios. Another example would be to multiply them both by 10, and this would give us 80/140. And we could go on and on. But the point is, all of these are equivalent. 8/14 is equal to 4/7, which also equals 16/28, 24/42, and 80/140. When we're working in our ratio tables, we'll be using multiplication or division to create equivalent ratios and solve problems. Let's take a look at our first problem. A zoo requires that one adult accompany every 7 students that visit the zoo. How many adults must accompany 28 students? One way to solve this problem is to use a ratio table. There are other ways that we will look at later in the chapter. In order to complete the table, we need to make equivalent fractions. We could add one adult and add 7 students each time to complete our table. So if there are 2 adults, we would have 14 students. We would need 3 adults for 21 students, and following the pattern, we would have 4 adults for 28 students. Each time we added 1 adult and 7 students. We know that repeated addition is the same as multiplication, so we can approach the ratio tables another way. Whenever we are using equivalent fractions, we want to either multiply both the numerator and the denominator by the same number, or divide both the numerator and the denominator by the same number. This ensures that the fractions remain equivalent. In this ratio table, we don't have those middle rows, and so we need to go directly from 7 to 28. You have to ask yourself, how do I get there? What can I multiply by, or what can I divide by? In this case, 7 times 4 is 28. That means I will also need to multiply the numerator times 4, and I can find that I need 4 adults for every 28 students. If you take the numbers out of the table, you can see that we're basically working with equivalent fractions, just in a different format. If the problem was set up this way, the one that I just drew, you would multiply times 4 and times 4 to make the equivalent fraction. And that's exactly what we're doing in our tables. Joni purchased 200 beads for $48 to make necklaces. If she needs to buy 25 more beads, how much will she pay if she is charged the same rate? When you're given a ratio table, sometimes there will be squares in it that you don't need to use. One way we could approach solving this problem is to simplify the fractions. There are different ways that you could do that. We could divide both 248 by 2, and we would have 100 over 24. We could then divide 100 by 4 to get 25, and on the bottom we would also have to divide by 4, and we would find out that it would cost $6 to buy the 25 additional beads. That's not the only way to solve the problem, though. We could also divide both the top and the bottom numbers by 4, and we would have 50 on top and 12 on the bottom. We could then divide by 2 to get 25, and divide the 12 by 2 to find that it would cost $6. We get the same answer even though we approached it a different way and used different numbers to simplify our fraction. Another way we could solve the problem is to simply bypass those middle boxes. We can get directly from 200 to 25 if we divide by 8. We can also divide 48 by 8 and learn that the beads would cost $6. So that was 3 different ways to solve the problem. All of them are correct, and all of them are valid and legitimate ways to solve the problem. Let's go on to the next problem. In this problem, Yolanda used 12 yards of fabric to make 9 chair covers. Find the number of chair covers she could make with 20 yards of fabric. If I look at going from 12 to 20, I run into a little bit of a problem. It's not easy for me to get directly from 12 to 20. There's nothing I can multiply by or divide by that will get me there in one step. If this is the case, I could do something called scaling. Scaling is a very fancy word for saying I can simplify the fraction. First, I will simplify the fraction in order to go forward again. So to simplify the fraction, I can divide both 12 and 9 by 3. And this gives me 4 over 3. Now I can get directly to 20 from 4. I know that 4 times 5 is 20, and 3 times 5 is 15. This tells me that Yolanda can make 15 chair covers from 20 yards of fabric. So as you can see, there are different ways that you can approach solving the ratio tables. The most important thing to remember is that we are working with equivalent fractions. So whatever you multiply the top number or numerator by, you must also multiply the bottom number or denominator by. The same goes for division. This concludes the lesson on ratio tables.